Welcome everyone, and very good evening. Do you hear my voice? Hello. Okay. Right. Okay. Thank you for our response. All right. So today we will continue our class again. All right. So basically, I'm sorry for the last week. Okay. We could not have a class on the Friday. Okay, due to my visit to industry. Wait a minute, ada call kejap. Alright, tak apa. So I would like to share my screen first. Okay, so we are still in chapter 1. Okay, okay, we are in chapter 1. Okay, I think do we have, okay, kejap, calibration error. Yang ni dah I think this is fine dah. Okay, so now we are going to go for a chapter on the part 3, okay, which is on the calibration, potentiometer and noise. All right, so basically for the calibration is the way to compare a given instrument against a standard instrument to determine its accuracy. Okay, what we mean as a calibration is we have one device and which is as a reference, okay, which is equal to the standard instrument, and we have another one which is what we have we usually use, okay, and then at certain time we need to calibrate the what we have already used, okay, in order to be same like a standard instrument, okay, that we call it as a calibration. Okay, so I think last time we learned about the standard. Okay, there is a premier, secondary, and tertiary. Okay, under that standard, okay, the bottom will compare the bottom device will, maybe I can show again about the standard. Okay, here, which is the working standard. Okay, the lower part will be calibrated compared to the secondary standard, and then the secondary standard will be compared to the primary standard, and the primary standard will be calibrated compared to the international standard. Okay, this is how the calibration will be done. Okay, especially for the usage in the industry. Okay. Okay, now, so for the calibration, okay, in this study, we will learn on the DC and AC voltmeter and how the calibration for the DC and AC voltmeter, and also for the DC and AC ammeter and ohmmeter, and other one is a potentiometer that also can be discussed for the calibration method. Okay, as the calibration for the analog instrument, in order to calibrate the DC voltmeter, a few instruments, okay, such as a voltage regulator, resistor, and the potentiometer will be used as the standard measurement instrument. Okay, and then that instrument, standard instrument will be which comply with the international standard, can be used to calibrate the measurement measuring equipment in the laboratories and the industries. Okay, this is how I said about the international standard that will be has a reference for the equipment for the laboratories or the industry to be calibrated. Okay, why the industries or the laboratories equipment need to be calibrated always? Why? Actually, because of in order to get the accuracy in for the equipment in the laboratory and industry, they need to always to what we call it to compare themselves as the reference one in order to make sure that there is no error along the usage of the device. Okay. And normally the digital instruments such as digital multimeters, okay, usually have high accuracy and high precision. However, and thus it can be used as the standard instrument to calibrate for the other analog instrument. Okay. So the digital multimeter normally it doesn't doesn't what we call it damage easier. Okay, then it can be used as a standard instrument for that. Okay, the digital. However, for the analog, it will have a lot of parts. For example, the the spring, for example, and for the magnet and also the mechanical part, and it will be have some damage throughout the year, and there will be need some calibration for that, or maybe repairing on the device itself. That's why for the analog instrument, it will be like this, where in order to calibrate the DC voltmeter calibration, the regulated DC voltage source will be supplied, and then there is also the voltmeter, which is that we use for the calibration, and also we have the standard instrument in order to measure the voltage. Okay, so you can see here there is a voltage resources, and at one point we measure by using the voltmeter, analog voltmeter, and another one is using the digital voltmeter, and then we can see the difference between both voltmeter, and from there we know that either the under test voltmeter is good or not. Okay, so the test voltmeter reading is compared to the voltage reading obtained using the standard instrument. Okay, so the same with the ammeter. Although the voltmeter is connected parallel, the ammeter is designed and detect and calibrate based on the series connection, which is the DC ammeter can be calibrated using the standard resistor R. Okay, standard resistor R, and then the standard voltmeter as shown in figure 1.2, where the test ammeter A here, okay, is compared to the calculated Ohm's law. Okay, based on the theory of the Ohm's law, how much we supply the V and how much the R. Okay, and we can know the A. Okay, V equal to IR. Okay, we can know the current. Okay, so once we know the current from the theory, then we can compare to the voltmeter ammeter that we connect. Okay, so this is how the ammeter calibration will be done. Okay, based on the ohmmeter, okay, the ohmmeter is used to measure the resistance, where the ohmmeter designed by using the ensemble meter movement. Okay, I think next when we study on the DC meter in chapter 2, we will learn on the ensemble meter. Okay, and how the ensemble meter movement will be done. Okay, and this is considered to be an instrument of moderate accuracy. Moderate accuracy means not so high accuracy, because of the ensemble is still the analog instrument. they need a lot of mechanical structure, and in order to measure the current. Okay, and the accuracy of the instrument can be checked by using the by measuring different value of the standard resistance. Okay, compared for example compared to the digital instrument, digital ohmmeter. And then for example a simple zero resistance, okay, 0 ohm calibration is done by using a connecting its probe together and adjusting the zero adjustment knob so that its pointer points that 0 ohm mark. I think you pernah tahu I will show you the ohmmeter, I call it the calculation. Okay, if you have seen the volt, I want to show you. Okay, normally for the voltmeter or ammeter or ohmmeter, okay, we have like a probe like this, okay. So in order to calibrate either the ohmmeter calibration is good or not, okay, we can touch the plus and minus probe, okay, together, and then we can see either the resistance value is 0 or not. Okay, if not a 0, then we need to calibrate that it's lah, because within the connection between the plus and minus should be no resistance. Okay, if we have the resistance on that, we what we call it non-accuracy lah, non-accurate measurement will be done by using this voltmeter. Okay, so you can see here a rough calibration for the ohmmeter. Okay, for example, you have the plus and minus. Okay, for the probe terminal 1 and terminal plus and terminal minus. Okay, we can put it together to make sure that it's a 0. Okay. All right, so this is the calibration of the ohmmeter. Okay, so here I show you the working principle for the DR meter. In these studies, okay, in these subjects, the DR concept or principle is very important for you to understand, because it will cover for through AC and DC meter in next few chapter. Okay, and then where if you see they are using the magnetic, okay, the fixed magnetic and also the rotating magnetic field, which is throughout the supply of the current, and it can provide movement of the arrow. Okay, so the working principle of the is based on the motor principle. If you know, the motor principle is like we have a what we call it a permanent magnet. Okay, and then we have the coil. We have the coil at the center, and we have the supply. Okay, in order to supply the current. If we supply more, and it can rotate more. If we supply less current, it will just very slow, right? Okay, if you have used the DC motor, okay, if you supply low current, and it will not move, or it will move a bit. But if you supply high current, it will move fast, or maybe it will be damaged because of the spec of the motor is not what you call it acceptable for the motor. Okay, so when the current carrying the conductor, okay, when the current carrying the conductor is placed in the magnetic field, okay, it is act upon by a force which tend to move it to the one side and out of the field. okay, it will move to the other side, okay, of the field. Okay, I think you have learned about the flaming, okay, jari flaming. Okay, then we can know that there is a okay, I will show later. Okay, okay, whereas flaming is you have the field of okay, like this, okay, which is here we have the conductor, how the how the conductor means the arrow of the pointer, how the it moves, and this is on the magnetic, okay, the magnetic field direction, and this is the direction of the current, okay. So how the current is going on into the conductor, okay. So from there we can know that if the current is going in, and if the value of the uh, maybe I can show you here. Okay, when the current is entering the conductor, and then when the direction of the magnetic is not is like this, for example, N and S. Okay, we can see that the direction of the conductor or the pointer will be going up. Okay, it, pada sebaliknya, okay, if the current is like going in, but the direction of the N and S is apa terbalik maksud tu opposite, and the direction will be going down. Okay, maybe you can check like from this figure. Okay, the direction of the current, for example, if going in, okay, yeah, this is going out, okay, and then when you see there is an N and S, okay, so we can know the force, the movement will be going up, okay. Oppositely, okay, if you have the current into going into the inside, okay, and we know that the N and S, the position of the finger for the N and S is oppositely, and we can know that the force will be going down. Okay, this will make the movement of the pointer to go based on the strength of the current. Okay. Okay, so this is the deflection of the pointer. Okay, this will be proportionally move. Okay, based on the amount of the current. Okay, because of the uh, because of the strength of the current will give a higher movement of the pointer. Okay, so for the AC voltmeter and the ammeter, okay, this instrument also can be calibrated, okay, using the comparison method, such as the same like DC instrument, okay, because the concept is still same, okay. And about the potentiometer, this the potentiometer is is like resistance, adjustable resistance, which is the loading effect of the instrument always influence the ultimate value of the measured parameter. When the potentiometer is used with a high input impedance, okay, for measuring the voltage or small loading effect will be still occurs. Okay, in order to uh, solve the measurement problem, we need to have utilized an energy which is supplied in the circuit by using the potentiometer, and the key operating condition for the use of the potentiometer is zero current when the circuit being measured. Okay, here there is a loading effect, which is the reduction in the value of the parameter of the circuit due to connecting of the measuring instrument into it. Okay, means based on the potentiometer, the resistance that have been adjusted. Okay, we call it as a loading effect. Okay, how much the resistance have been loading into the circuit. Okay. Do you know the potentiometer? Have you seen potentiometer in your life?
Yes, Doctor.
Okay, I think it's very common. All right. Maybe some of you doesn't know. Okay, this is like a potentiometer. Okay, I think everywhere now has this. Okay, and even I think for analog, for example, to higher the sound of your TV, maybe like previously they used like this, but now I think always using the button right now. Okay, sometimes for the to change the channel in your radio, still using this, but sometimes now they are using already use a button. Okay, to change the what you call it, the channel. All right. So this is the how the potentiometer works. Okay, where the potentiometer is shown is like this, where there is a voltage supply, and then there will be a high resistance wire that will be uh, that will be used in this figure. Okay, where the high resistance wire is connected in series with the voltage source. Okay, and with the steady current in this wire will produce the uniform voltage drop along its length. Okay, that means if the length, okay, the voltage drop between the movable contact between X and Y will be directly proportional, okay, to the length of the wire between the point X and Y. Okay, so that means the voltage drop will be across the unit length of the resistance. Wire depends on the circuit current that can be changed by varying the rheostat R. Okay, the rheostat R here is like a potentiometer, how you can adjust it. Okay, and then the voltage drop will be changed. Okay, drop from X to Y. Okay, it depends on the either the if it's here means low resistance. Okay, that means it can be go back to the here. Okay, but if it's high resistance and the wire will be the movable contact of the X and Y will be dropped. Okay, and based on the potentiometer, as I show you, there is a single range dial. Okay, that's a single range dial, and also there is also the slide wire and also the volt box. Okay, the slide wire, I think there is. Have you seen this or not? Okay, like this. Okay, which you can change. Okay, change the resistance by sliding it. Okay, like this. Okay, you can slide it to increase the voltage, to increase the resistance or not. Okay, and sometimes they are also like this. This is like wire. Okay, currently they have like this. What call it? Strain gauge. The strain gauge also one of the potentiometer. Okay, based on the force that have been detected from the strain gauge, the resistance will be increased or less. Okay, and will change the V equal to IR. Okay, this is one part of the potentiometer, but this have been changed the function into a sensors. Okay. Okay, so for the slide wire potentiometer, okay, for initial measurement, the potentiometer will be calibrated with one standard value. Okay, when in this calibration process, when the switch is closed, okay, when the switch is closed, the working current will flow through the slide wire and rheostat. Okay, so you can see here when the switch, see here when this switch is closed, and it can go to directly to the this circuit, okay, without this for the optional and the calculation. Okay, wait, saya angkat call sekejap. Okay, sorry, my mom call. All right, so on this is the basic circuit, okay, for the slide wire potentiometer, where the you can see here there is a working battery, and this is the slide wire from X to Y, okay, or like this, X to Y, and then we have the rheostat, okay, to change the value of the resistance. Okay, so if you see here, the value of this current can be modified. Okay, value of the current can be modified based on the rheostat. Okay, because V is fixed. Okay, fixed. For example, you put 5 volt, for example, and based on the R, when it become higher, the I will be lower. Okay, so we can change the value of R here, and it will change the current that will be going through in this slide wire. Okay, when for the calibration method for the potentiometer by using the potentiometer, okay, here the switch S, okay, we can see there is a switch here. When is S is connected to the cal, okay, calibration, okay, the K key, okay, the K key will connected to the sliding contact on the X, okay, and this is how the connection between the call it for the potentiometer slide wire. Okay, when the K is connected to the sliding contact X, and there is around 1 centimeter from the end of the slide wire. Okay, 1 centimeter from the end of the slide wire. At this point, the rheostat will be adjusted to make sure that the galvanometer indicates zero or no deflection. Zero means zero because galvanometer is detecting the current. Okay, so it means 0 ampere. Okay, if it's indicated as 0 ampere, means there is no current connected to the back to the that means there is no current detected lah. Okay, in this now condition, okay, the voltage at the point of X, okay, we call as Vx, the voltage for the Vx at the length of L1, okay, is equal to the standard cell, okay, which is the ES, okay. So we know that there is the connection will be like this lah, okay, where the slide wire, the X, Vx, and the cal will be connected like this, okay. So we know that the voltage for the point X is a ES, okay, ES here. Meanwhile, when we have the unknown measuring method, okay, which is when the S is connected to the OP, okay, to measure the EX, OP, in order to measure EX. EX means there is unknown measuring method, okay, which is we don't know, okay. We want to measure the EX, okay. So therefore, the sliding contact K, okay, will be adjusted until the galvanometer indicates 0 or no deflection. And at this point, the point Y and the length of the slide wire is L2. Okay, here we can see that when it's sorry ya, kejap saya ambil slide yang nampak benda ni. Dia terlari lah. Sekejap, mana slide dia? Tak kuliah. Sorry ya, wait a minute. Okay, macam okay. Alright. Kenapa dia macam lari? Okay. So basically, sorry ya, tadi saya punya slide tu terlari ya. Okay, so basically when the S is at OP, this is how we can measure the unknown for the EX. We want to know that the unknown voltage for the EX, then we can connect the switch to the OP, okay, which is the operate, and then the sliding will be directly to the Y, okay. Okay, so when we put okay, adjusted until the galvanometer, okay, indicate 0. Okay, so you can say like this, when the pointer, okay, for the slide wire, we can adjust the value of the slide wire, the length of the slide wire from X to the Y, in order to measure, to make sure that the value here is 0 or no deflection, okay, for the galvanometer. Okay, when we already get the indicator to 0, okay, then we can say that the length of the Y is L2, and we can say that the voltage that can be measured for the EX is equal to the ES times to L2 over L1. Okay. Last time we have known that the ES is Vx is equal to Vx is equal to the Es over L1. But now we don't know the value of the Vx, and we want to have Ex. That's why the Es we already known is times to L2 over L1. Okay, because L2 we know by measuring the slide wire, and L1 is measuring the slide wire for the X. Okay. Okay, this is the example, okay, for the potentiometer, which is the slide wire here is a 200 centimeter. Okay, for example, we have a 200 centimeter wire, which is the overall resistance will be 100 ohm, and the battery is 3 volt. Okay, the battery that we use is a 3 volt working battery. Okay, in this instrument, okay, the standardized reference voltage is 1.019 volt is given, and the sliding contact is 101.9 centimeter during the calibration process. Okay, that means when during calibration process, okay, which is the ES, okay, the L1 is a 1019. So we know that here is a L1. Okay, L1. Okay. Okay, this is the L1, and this is the ES. Okay, the reference voltage for this is a 101.9 volt. Okay. So now the question is want you to calculate the working current, and also the measurement range, and also the value of the rheostat value. Okay, so we can see how the example will be solved. Here, as I said, mentioned before, the L1 is 101.9 centimeter, and the LAB is the slide wire length. Okay, which is will be through this slide wire. When we connect it together directly, the value is of the resistance of the wire is 100 ohm, where the ES is 1019 volt. Okay, that have been given here. Okay, this is ES. All right. So here, when we want to measure the working current, okay, in order to measure the working current, we can use the value for the overall wire, which is the 100 ohm. When we get when we use the value of 101.9 cm, the L1, the value will be can be calculated like this, where we can calculate 100 to 101.9 and divide to 200, and we can get the L1, and then we can get the 50.95. Okay, we can just put like a ratio based on the length and the voltage that have been length and the resistance that have been given. Okay, because when the length is short, the resistance of the slide wire also will be reduced. Okay, because when the length of the wire is long and is higher resistance, when it's short, it will become shorter or reduced. Therefore, we can get the RL1 is to 50.95 ohm. Okay, here for the working current, we can know that at this point, the ES is 1.019 0.019 volt, then we can divide by R, okay, by 50.95. Then we can know that the working current, okay, throughout this part, okay, the working current here is a 20 milliampere. Okay, this is how we can compare. We can calibrate. Okay, we can calibrate, and we know that the value of the current that have been working in this circuit. Okay, based on the length and also the resistance. Okay, and next we want to know the voltage for the VAB. Okay, between this area, because when we have the RAB for 200 centimeter is 100 ohm, then we can know the RAB, okay, the VAB. So to know the VAB is very simple by using the Ohm's law, okay, because during the current go through this slide wire is 20 milliampere, and we can directly calculate times with the 100 in order to know the 200 centimeters for the AB, because they say about the AB, so we can determine based on the length, the full length, and once we determine by the full length is a 100 ohm, and we can directly calculate it, and we got a 2 volt for the V to AB. Okay, the voltage for the A and B is a 2 volt. And then how to determine the rheostat. Okay, the rheostat value. At this point, we can calculate the V working. Okay, V working based on the is equal to V rheostat. Okay, here V working is a V for the work battery. Okay, for working battery, and then the V rheostat is where we want to find. Okay, because V equal to V1 plus V2, right? For the series. Okay, for the series, V equal V1 plus V2. For example, if you know that working battery is V, VT, V total is V1 plus VAB. Therefore, for the V working, we already know that 2 volt is a value, and the V V working is the 3 volt for the working battery. Here is given. Okay, 3 volt, and then minus to VAB that have been calculated in B. Okay, and then we can know that is a 1 volt for the rheostat. Okay, at this point for the rheostat, by using the Ohm's law, V equal to IR. Therefore, we know the V rheostat is 1 volt, and the I work, the current here, the working current is 20 milliampere. Therefore, we can find that the resistance value is a 1 over 20 milliampere. Then we can get 50 ohm for the rheostat. Okay, at that state. Okay. As I mentioned before, okay, during this calculation, don't forget to put the what we call it, the units, either the volt, ampere. Even for the ampere, you should carefully put either in milliampere or ampere, or maybe for the microampere. Okay, so please make sure that the unit is correct. All right. Okay, that's one for the single for the slide wire. However, for the single range dial, okay, that will be a different method. Okay, where in this potentiometer, the single range dial is known as 2 dials, which is variation of slide wire potentiometer. Okay, basically, the practicality compared to the slide wire is based on it can decrease the physical size of the meter. Okay, sometimes we have a limitation on the size. For example, the box that we want to put the potentiometer itself. For example, like in radio, for example, okay, we cannot put the slide wire because slide wire is very long. Okay, therefore another type, which is the single range dial, like this, yeah, like I shown before. Okay, can be used because of the limitation of the box or the size of the sheet, the box. Okay, the reading also can only take in short time. Okay, because of we don't have to slide from A to B. For example, if you see there is a 200 centimeters length from A to B, you know how long is it, and it's difficult to slide from here to here. It's very fast. Okay, therefore they develop a new potentiometer by using a single range dial, and it's easy to twist. Okay, it's easy to twist the the toggle. Okay, and then we can without moving it from A to B at long range. Okay, and it will be in a short time. And the accurate reading also can be obtained because the reading value can be taken directly from the needle point on the both dials. Okay, on the both dials too means the at this point. Okay, for example, at this point, or maybe we can show you. What is potentiometer? Okay, so the potentiometer here, you can put, for example, pointer. Okay, then we can know that the pointer is going up or down. Okay, and we can know that the value of the resistance is going up or lower. All right. So here, this physical form is similar to the slide wire potentiometer, and the difference is only the arrangement of the slide wire is on the horizontal or in long arrangement, but for the physical form, the range dial is more on the circular. Okay, like this. Okay, this is how the basic construction of the slide wire uh, of the single range potentiometer, which is in this single range potentiometer, there's some checkpoint, okay, in order to measure each resistance, and this is based on the slide wire. Okay, for example, the main dial and the slide wire is like you make a slide wire, the long slide wire into a circle. Okay. Okay, based on the calibration method, in this calibration method, we want to setting the direction needle. Okay, the direction needle, like this pointer, okay, of the main dial and the slide wire dial to the standard voltage value. Okay, so for example, if we put, okay, the standard cell, okay, for the battery, okay, which is the 1.019 volt. Okay, then we can directly need the needle in the main dial. We can distribute it. We divide it into 10 stages, for example. Okay, 10 stages. Then we can know that for each stages will be divide into 1 volt times bahagi divide into 10, then we can get for every station will be a 0.1 volt. Okay, as I said before, in series connection, the V total is equal to V1 plus V2 plus V3 until V10, and then each of the V1 and V2 until V10 is 0.1, and then all 0.1 times to 10, we can get back the V total is 1.019 volt. Okay, here, as you can see, the setting of the direction needle of the slide wire to the division of the 19. Okay, for example, in here, 19, if had a 100 V division, that can be stepped to slide wire. So as you can see, okay, the value of the battery, for example, 1.019 volt is equal to 10 volt of the dial. Okay, 10 volt, 10 volt, 10 times to 0.1 volt is 1 volt, and another one for the rheostat, for the slide wire dial. Here we put as to make sure that we have a 0.19 volt. Therefore, we can get a 19 times to 0.1 divided by 100, and then we can get the battery. Okay, the voltage for the standard cell is 1.019 volt. Okay, so here the main dial is for the main voltage, which is here. We divide it into 10, and we can get for 1 volt for here, and another 0.19 volt is from the slide wire dial. Okay, so here, as the single range dial potentiometer calibration method is the same method like the slide wire. Okay, because we have the CAL and also OP. Okay, for the ES, and also for the EX. Okay, we can operate with the OP. Okay. All right. So for the calibration, we can connect the switch here, okay, to the calibration source, okay, connected to the ES, okay, and then it connect to the ES, and the rheostat will be adjusted. Okay, this rheostat will be adjusted in order to have no deflection in the galvanometer. Okay, no deflection. Okay, so in this part, when the zero reading is indicated, okay, on the galvanometer, the protection resistor must be short circuit. Okay, which is then the rheostat will be adjusted until no deflection again. Okay, so here there is a we'll call it the protection resistor. This will be a we'll call it short circuit, and in order to make sure that this rheostat will be adjusted again. Okay, in this part, this is for the measuring the unknown voltage. Okay, for the EX. Okay, so for the EX, the connection between the OP, okay, between the switch is to the OP, and then we can get the EX, and then directly to here, and we can get the value from the main dial, and also the slide wire dial. Okay, so we can measure the value of EX, which is recorded by adding the value read from the main dial and the slide wire dial. Okay, here this is the example how it's work. Okay, it's more easier to understand. Okay, on how to calculate the for the simple single range dial. Okay, in this example, Okay, a 2 dials potentiometer, which is the main dial, and the slide wire dial is used. Okay, and there is a 20 stages. Okay, in this part we know they're using 20. They are given 20 stages of main dial. Okay, that every stage of the dial is a 10 ohm. So if 20, that means a 200 ohm lah, for the main dial lah. Okay, because 20 times to 100 now 10, and we can know that 200 ohm lah. And with each stage represent 0.1 volt. Okay, as he said, okay, as given, one stage is 0.1 volt. If 20 stage means a 20 is 2 volt. Okay, because 20 times to 0.1 volt. Okay, and a slide wire resistance is 10 ohm. Okay, this all is a 10 ohm, and we have a division for this is a 200. Okay, 200 division. Okay, which is there doesn't have a stage like this. Okay, this is just a slide, and the working battery is we are using is 6 volt. Okay, therefore the question is used to calculate what is the working current. Okay, based on the working current, and also the measurement range, and also what is the rheostat value. This is the almost the same like when we calculate for the slide wire potentiometer. Okay, which is for the working current, the measurement range for the VAB, and also the rheostat value. Okay, the way how to do it is based on the, we know that the resistance for each is 10 ohm, and then we have times to 220 because we have 20 stages. Okay, then we know that for the total resistance, okay, total resistance is 200, and this is 10. Okay, is given as 10. So the total resistance for this is 210. Okay, so this is for the total resistance, but for the working current, okay, we can know that every stages have already given 0.1 volt, and every stages also the resistance is 10 ohm. Therefore, we can directly get the current, which is by using the Ohm's law, V equal to IR, okay, which is I equal to V over R, and we can directly calculate the 0.1 volt to 10, and we can get 10 milliampere for the working current. Okay, the working current between one part and one stages to one stages is a 10 milliampere. Okay, for the measurement range, because we want to have a Vmax, okay, what is the Vmax? Then we can know that the overall RT for this both main dial and the slide dial is 210 ohm. Therefore, the 10 milliampere, okay, can be calculated directly to the 210 ampere, 10 ohm. Okay, because why? Because you know I equal to VR, V over R. Then we want to know V equal to IR is V equal to IR is to 10 milliampere, just times to 210, and we can get the measurement range can be 2.1 voltage. Okay, full measurement range. Okay, next is for the rheostat. Since we already know the full measurement range is 2.1 volt. Therefore, we want to have we want to know the rheostat itself. So the rheostat is based on the working battery, which is 6 volt, is given here. Okay, and Vmax, okay, Vmax mean from here to here, okay, from here to here is 2.1 volt. Then we know that rheostat is 6 minus to 2.1 volt. Okay, when it's calculate like this, we can get the V for rheostat is 3.9 volt. So here we can say that, since we already know the I work is 10 milliampere here, okay, then we can directly divide the 3.9 volt into with the 10 milliampere. Then we can know that in this rheostat, the rheostat value is, the maximum is 390 ohm. Okay, so that's for the single range dial. Okay, I hope you can understand what I'm saying for the how to calculate. Okay, okay. Normally the question is play around on this three things lah. Okay. Okay, next is the volt box potentiometer. Okay. Where is the volt box is used to expand the voltage measurement range of a basic potential meter circuit. We do that in a box, okay, and it use voltage divider concept, okay, by using the divider concept here, okay, based on the R1, R2, R3. This is not used, for example, for the potentiometer, we have just one slide wire, okay, okay, for the slide wire, but for the single range dial, because of word dial, the structure is like a dial, okay, but that's only by using a stages. In this part also we're using the stages, but each stages is already have a R1, which is the ohm, which is the resistance for each stages, okay, and a proper range of resistance must be chosen so that the output voltage from the volt box is not more than the measurement range of the potentiometer. Okay, and then the resistance value in series must be added respectively for the every range. Okay, so R1 plus R2 plus R3, R4, R5, and we can get the R total. Okay, the same like this lah. Okay, for example, for each stages is 10. Then if you have 20 stages with the same 10 stages, it will be 200. Okay, 200. Okay, the same like this. If we put R1 10 and each of R is 10, then we can know that here the RT will be 50 because 10 times 2 R times to 5, then we can get 50 ohm. However, in this case, might be the resistance value for the each of the resistance will be different. You can put different R. For example, here 10, here 20, 30, 40, 50. So we can change, okay, the voltage based on the output that we want to have. Okay, for example, if we want to have 10, then we can get that 10 only. But if you want to have 20, you can have only 20 on this part only. If you want 30, and then 10 plus the 20, and we get 30 lah. Okay, this is how, okay, the volt box, okay, like a box, we can choose what the value that we want to measure. Okay, here, when we want to design a volt box for measuring the range for the 5 volt, 10 volt, 50 volt, and 100 volt, and each resistor is a 30 over V, okay, which is the volt box is used together with a potentiometer with a range 1.8 as shown below. Okay, so we have the potentiometer for 1.8 volt potentiometer, okay, and to find the voltage for the 5 volt, okay, for if there is a R1, we use R1, and 1.8 will be times to 30 ohm because we want to find the R1. Okay. Okay, because it said already the potentiometer with range of this is 1.8, and then we can just calculate with the resistance, and then we can get a 54 ohm. Okay, for the R1. Okay, because of the we want to find the VR R5. Okay, so which is VR4, VR2. And we know that the 5 volt, okay, for have been given, okay, in this part is 5 volt minus the 1.8, okay, and we can know that there is a 3.2 volt, okay, for that has been crossing through the R1. And in this part, if you want to know the VR2, okay, okay, so here you see there is a 5 volt, 10 volt, 50 and 100, right? So because of 5 volt minus to 1.8, we can know that the voltage that cross to the R2 is 3.2 volt. Therefore, if we know the voltage, the resistance of this part is 30 ohm over V, then we can just calculate the 3.2 volt times to the 30, and then we can know that R2 is 96 ohm. It's the same for the 100, okay, 110, which is 10 here, 10 minus to 5 volt, and we can know that the voltage that will be crossed through the R3, okay, then we know that because of 10 minus to 5 volt, we know that 5 volt through the R3, and R3 is a multiplication of the 30 ohm to 5 volt, and we can know that the R3 is 150. Okay, it's the same until the 100 volt, the same principle. Okay, first you need to minus, okay, you need to subtract 10 volt to the 5 volt, okay, to know the difference between this voltage. Okay, then we can just time to 30 ohm per volt, and then we can get the value for the each of the arm. Okay, so here is just to design the voltmeter, okay, based on the what is the best resistance value that can be put in this part. Okay, so I think the potentiometer is already covered. Now we are going for the noise. Okay, I think every one of you already know about the noise. I think if you already learned about the signal and system, I think there are a lot of discussion that have been discussed for the noise. And I think in 4th year, you will have subjects for the communication system. Also, we will cover the noise. Okay, but this part we just know on the principle or the theoretical of the noise. Okay, the noise is the unwanted disturbance, okay, in the electrical signal. Okay, usually when the signal is no noise, it will be clean like this. Okay, it will be clean like this. If you see from the what we call it, the oscilloscope, okay, it will be clear and clean like this. But if there is a noise inside the signal, it will be a zigzag like this. Okay, this is a signal with noise, this is without noise. And the effect of the noise is like this, where there is a category of the noise where there is two types, which is the correlated noise and the uncorrelated noise. Which is the noise that exists only when signal is present, is called as correlated. But for the uncorrelated noise is without signal, the noise is already there. Okay, without the signal, The noise is already there. So for the correlated noise, a form of internal noise that is correlated to the signal and cannot be present in a circuit unless there is a signal. Okay, this is what I mentioned. And it can produce the nonlinear amplification. Okay, nonlinear amplification resulting in nonlinear distortion. Okay, because when its signal come, okay, there is some effect from the others, from the device, and it can give the nonlinear amplification. Okay, and for the nonlinear distortion, we cannot predict, okay, the value or the output that will be measured at the end. Okay, there is two types of nonlinear distortion based on the unwanted frequencies. For example, there is a harmonic distortion, and also there is a intermodulation distortion. Okay, based on the harmonic distortion, it comes from the unwanted harmonies. Okay, when we call as harmonies is can produce the nonlinear amplification, which is the original signal in the first harmonic, okay, will be affected by the 2 times of the fundamental frequency in the second harmonic and also the third harmonic. Okay, we can see that the harmonic is like this. Okay, when there is a input, okay, there is a second layer or third layer of frequency spectrum that have been harmonized, that can be distorted by the noise. This is where the input without the noise. When it comes the noise like this, the distortion from the harmonic distortion, it produces the second, third, or fourth harmonic distortion. Okay. And another one for the intermodulation distortion is based on the two frequencies that are very near to each other, and it will give a different intermodulation distortion based on the effect of both signal. Okay, so the intermodulation is a generation unwanted sum and different frequency produced when two or more signal mix. Okay, the word is mix. Two or more signal mix, then it produces the intermodulation distortion based on the sum and difference, sum and subtraction. Okay, for example, like superposition. Okay, so this plus with this, you can get the V sum, but V2 minus to V1, you can get a V difference. Okay, this is called intermodulation. Okay, that's for the correlated noise. That means when it's come a noise, a signal, there come the noise. But on the other hand, there is a uncorrelated noise. Even though we don't have the signal, the noise is already there. And it can be categorized into two types, which is the external type for the uncorrelated noise and also the internal. Which is the external is outside device, while the internal is inside the device itself. Okay, so you have a circuit, okay, without any signal on, or the internal noise is already inside the circuit. Okay, the internal can be produced based on the thermal. Thermal means when you operate the circuit is too long, then the noise will be occurred. And also short. Short means short circuit, for example. And also the transient time between the, for example, the, how we call it, the frequency in the oscillator, for example. Okay, the transient time, it will give a vibration in the circuit. However, for the external is based on the atmospheric, okay, based on the environment noise. the extraterrestrial, okay, and also based on the man-made. Man-made is maybe you put some things, okay, based on the circuit, for example, and it'll be man-made. Impulse and the interference means when we bring two device uh, near and it will interfere to each other. Okay, for example, you call the near to the radio, and then the radio frequency, the radio will be interrupted by the interference from the mobile phone. Okay, for the external noise generated outside the device, okay, from the environment, from the lightning, for example, okay, originating in each earth atmosphere, such as lightning, okay, when it's come to lightning, sometimes it's mengganggu, okay, disturb the signal inside the circuit itself. And we call it as a static electricity, okay, based on the sputtering, for example. And also for the extraterrestrial, okay, based on the outside the Earth's atmosphere. This is inside the Earth's atmosphere. This is outside the Earth's atmosphere. For example, from the solar, from the what we call solar is from when it's come a nebula explode, okay, from the sun, okay, then we call it a solar noise, and it generated directly from the sun heat, okay, the explosion in the sun. And also we also have the cosmic noise, okay, based on the galaxies, okay, but it's very rare lah, okay, very rare. All right, and for the man-made is produced by mankind based on the spark produced mechanism, for example, and automobile emission, okay, the switching and etc. And mostly occurred at the more populated metropolitan or industrial areas, okay. So we need to have the isolation, okay, to reduce the noise based on the mankind, based on the noise from the vehicle, for example, okay. And impulse noise is the high amplitude peaks of short duration in the total noise spectrum, okay. There is an impulse, sometimes it's come immediately, okay. And for the external noise, there is an interference, okay. This is what I said before, like a radio frequency spectrum, and when you talk with the handphone near to the radio, there will be an interference between each other. Okay, for the internal noise, this is inside the device or circuit. For example, the thermal noise, okay, from the conductor to thermal agitation, excitement, and also there is also short noise. Okay, short noise is from the holes and the electron between the inside the electronic device. Okay, that produce the short noise inside the device. Okay, this is more on the molecule part. And also for the transit time is on the random variation on the stream or the carrier of the pass into input to the output device. Okay, so this is more on the internal noise. Normally, there are two of these is commonly occur in the device. Okay, for example, for the thermal noise and the short noise. Therefore, I think you will learn on the low pass filter or high pass filter in order to cancel out the noise, okay, inside the device and also inside the maybe from the outside, okay. Okay, I think that's all for chapter 1. Okay, that's all for chapter 1. I think there will be another on the chapter 2. I think next chapter 2 I will go for next week, okay. based on the DC meter. Okay, so I think for you, you can start your tutorial. Okay, you can start your tutorial for the chapter 1. Okay, and to submit it, you can submit it together with the chapter 2. Okay, chapter 2 together. Okay, so please do it because I think it's quite a lot. Okay, quite a lot. And you can see the example that I discussed in the slide, and you can try it by your own. Okay, okay, I think that's all for today. Is it okay for you?
Okay, sir.
Okay.
Alright, sir.
All right. Before we finish, I want to take the attendance. Is it okay? Oh, 64%. Okay. Download attendance list. Wait a minute. Download. Okay. I think that's all. Okay. So see you next week. I think we will do it on Friday next week because I have a bengkel, a workshop on Monday and Tuesday. Okay. So I will meet you again on Friday next week. Okay. The same time like today. Okay. Thank you all. Okay.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you.
Okay. Yes. Assalamualaikum.
Thank you, Doctor.